I want to talk about some more examples of mappings, transformations, functions in the most general sense that we're going to do them from some Rn to Rm. Um, I've been showing some examples of R2 to R2 because that is new compared to curves and just functions with one output. But I want to just go a little bit beyond that. So, for example, one great example that we've learned just recently, well, let's call it T, I guess. I've been using T for transformation instead of F for function, but it really doesn't matter. Um, from R3 to R3, just like polar is a really good example of a transformation from R2 to R2, spherical coordinates. So we've got rho, theta, and phi, and using one of the mathematician's conventions, we go x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. That's going to be our x, y, z. That's the spherical coordinate transformation. And so we can think of it either as a different way of describing just one space, but we can also have this somewhat more abstract and powerful point of view of a transformation that takes the coordinate numbers essentially to a physical point. And so it's going to look a little weird to have like rho, theta, and phi, but it totally makes sense. And remember, rho is never going to be negative, so we don't need the stuff back there. Theta only goes from 0 to 2 pi, and phi only goes up to pi. So it's going to be kind of this box-like region going off infinitely far in rho, but finite in both theta and phi. And that's going to map to three-dimensional space. So for example, let's see. Yeah, let's keep the formulas. What happens if we just look at what's the nice thing to do? Well, we could take a curve here. We could take the curve maybe where phi is equal to 0 and theta is equal to pi over 2, and then rho is anything, and take, what does that correspond to? Well, we should be able, if you think about spherical coordinates, you should be able to know what that means, because these guys have a geometric meaning for us. Polar angle 0, azimuth pi over 2, and any radius. But let's just go ahead and get it out of the formulas as well. That's going to be the parametrized curve where we take some number rho, and then we just take that to, let's see, sine phi is 0, so we just get 0, comma, 0, comma, and then cosine phi is 1. Now, of course, the pi over 2 actually didn't matter there. You know, I'm going to switch that. That's not as interesting. How about pi over 2? Pi over 2. I forgot that would just be silly. So now it's going to be 1 and 0, 1 and 1, and then, well, it's almost as stupid. But we've got, now it's going out in this direction. It's just the curve that starts here and goes out in this direction. And that makes sense, because phi is pi over 2 means polar angle pi over 2 coming down the xy plane. Theta equals pi over 2 means crank this way, and any rho means go out radially any distance. But we didn't have to know that. We could just plug it in and just take two of the variables to be specific values, and then we get a parametrized curve. Now, it's more interesting if it's not like a linear curve, like a straight line. If we have, like, let's see, remember this was rho, theta, and phi, the way I was doing it. If we had rho is some value, and let's say phi is some value, so rho and phi are given, and I just take theta to be anything from 0 to 2 pi. So let's say rho equals 2 and phi equals pi over 4. Okay, then where's that going to be over here? It's going to be, now the variable is theta, and that goes to 2, because rho is 2, and then sine phi is just root 2 over 2 times cosine theta, and then rho sine phi is still, again, just root 2 when these cancel, times sine theta, and rho cosine phi is, again, just root 2. Okay, so it's in the plane z equals root 2, and it's a circle of radius root 2. Oh, surprise, surprise. That's what we get if we take the sphere and we take a latitude line on the sphere. And so this bunch of thetas just cranks around the latitude line, like it's supposed to. If rho is fixed to be 2, we're on a sphere of radius 2. We fixed the polar angle, so we fixed the latitude, but then the longitude is varying. But again, it can just come out of just the formulas. So curves here, straight lines here along the coordinate axes turn out to be latitude, longitude, and radial curves. Okay. So what about coming backwards? Well, that's what we do all the time when we set things up in spherical coordinates. We have a region, like I'm looking at the region inside this hemisphere of radius 2, but outside this hemisphere of radius 1, and let's say it's only this part in front of the YZ plane. What's the region in rho theta phi space that corresponds to that? Well, that just really corresponds to finding the rho theta and phi that sets up that region in spherical coordinates. So I'll skip that example because we're pretty familiar with that right now, of doing that. Well, a variation of that, though, is where we get to our first example so far of just going from R2 to R3. We're going to be doing this a lot, where we parameterize surfaces, but I want to mention it right now. Suppose we just set once and for all rho to be 2, and so it's not a variable anymore. And I just have 2 here, 2 here, 2 here. Then what does that do? It's got theta and phi space now. Okay, theta still goes from 0 to 2 pi. Phi still goes from 0 to pi. It's just this square, and that parameterizes just a subset of R3. It's going into R3 still, but it's definitely not filling out all of R3. So it's not onto. That's terminology we've had from the linear algebra stuff. It's not onto. It just exactly hits just one sphere of radius 2. But it covers the whole thing because I've chosen to use all the applicable phi and thetas. Okay, so that's a new kind of map where we are not trying to fill out all of the target as a coordinate system for the whole target. We're specifically parameterizing just a surface that's part of that. Okay, so this is a parameterization of the sphere. Very much like we had curves that were parameterizing geometric curves by having a variable mapping in. This is the two-dimensional analog of that. So that's going to be something we're going to be talking about a lot in the next chapter when we use that to do flux integrals and surface integrals. So the one thing I haven't talked about so far at all in these lectures is where n is greater than m. Okay. But we've had that. We've had plenty of things like that. Now I'm going to use f because it feels less like a transformation, like R2 to R. And so, like for example, xy goes to x squared plus y squared. It's just a real valued function. We haven't thought of that as a transformation so much, but we certainly can. It has a kind of a simplistic output. It's not very geometrically interesting, but it's still a transformation. Okay, and well, let's have a name for that. Let's call it v, maybe. Okay, so here's the v number line, and here's x and y. And then the question was, how did we picture this? What was geometrically going on? Well, you can certainly take points. You can take like the point 1, 1, and that's going to map to 2 over here. That's not terribly exciting. We could take a curve over here and map it to over here, but it'd be pretty boring because it would just be, it's just not much place for it to go. We could figure out how much of the real line it covers. It's somewhat interesting, but it's not that great. for these kinds of maps where you're going from a big space to a small space, this is where, again, going backwards is really, really the most interesting thing. And I claim we've been doing that a lot. Well, what are the only kind of simple subsets of R? They're points. We're not going to take lines and regions inside of R. There's no such thing. And what does it mean to take all the inputs? Let me just erase this real quick. What does it mean to take all the possible inputs in here that go to, for example, 1? Okay, it's a level curve. It's just all the x's and y's such that x squared plus y squared equals 1. And so it's the unit circle. Or if I looked at 2, that's where the radius is square root of 2. We've been doing this ever since we started dealing with functions of multiple variables. It's called taking level curves. Okay, and so this process of pulling back subsets and looking at where they came from in the source is something we've actually been doing a lot here. And so it's just I'm just trying to tie that in to the more general thing. So and then the last example would be just the same kind of thing, but maybe if it was like R3. If you have a function from R3 to R1, maybe to make it more interesting, f of x, y, z is x squared plus y squared minus z squared. Remember what the level sets of those guys looked like. If this was positive, we get a hyperboloid of one sheet. If it's 0, so if it's positive or 0 or negative, those are the three cases. If it's 0, we get the double cone. And if it's negative, we get the hyperboloid of 2 sheets. It kind of sits inside here. Okay. And we get a whole family. For all the different values, we get a family of hyperboloids where there's one black sheep in the family. It's actually a double cone. It's a singular surface. And we're actually going to think a bit about what was special about this number that has to do with calculus that means they pinch down and gets a nasty kind of singular point there where it's not smooth. And that's going to have to do with what's called the implicit function theorem, which we're finally ready to talk about in a little bit more generality. And so this is another case where we've got R3 mapping to a boring space, but it's still interesting to take various different numbers, negative, 0, positive, and look at the inverse images of those single points, and we get very interesting stuff. That's not trivial at all.